Hello everyone, and welcome to this visual summary of our research in Making the Discrete Continuous, where we present results of an industry-academia collaboration co-funded by University of Glasgow and Dotphoton through the Centre for Doctoral Training in Applied Photonics. The pipeline used by modern cameras to capture the incoming light from a 3D scene into an image is far from simple. After going through camera optics, the information captured through the CMOS sensor still needs an image signal processor or ISP to become a post-processed RGB image. An intermediate output of this process achieved right before the ISP is an unprocessed raw image. Raw images present several advantages over RGB besides being faster to obtain. They contain physically meaningful information with little to no interventions, respecting the well-known noise distribution that can be encapsulated in the Poisson-Gaussian model. Raw images have higher bit depth, and as such they have the capability to capture and preserve more information than RGB. This might be some of the reasons why training on raw images has led to better AI performance in challenging conditions such as rain, fog, or low light. Despite this success, real raw datasets, as any real datasets, are discrete in nature. They are made out of individual images that represent only a limited set of values sampled from any continuous variable such as the irradiance, in this case expressed as the mean number of electrons inside the bounding box of each Person instance. Because of this discrete nature, the sparse and imbalanced distribution of real data can lead to long-tail and out-of-distribution generalization problems. This can be particularly troublesome for AI agents that interact with humans, such as those in autonomous driving, since a low real data density in dark traffic scenes could lead to pedestrians going undetected, causing accidents. Due to its discrete nature, evaluation of performance on real data faces limitations. Low-density regions of the ground truth distribution require us to cover a larger interval of any continuous variable of interest to gather the same number of data points as in shorter intervals of high-density regions. However, with synthetic data, with high-quality, physics-aware synthetic data that is only possible through data augmentation on unprocessed raw images, with such synthetic data, we can fill low-density regions of the distribution in a controlled way, generating as much data as we need, constrained only by computational resources and not by the troublesome task of real data collection, which could be impossible for safety-critical scenarios that are dangerous to replicate. In this way, synthetic data effectively makes the discrete continuous, enabling a fine-grained characterization of AI performance in challenging conditions. This improved resolution and controllability allows us to uncover issues that would otherwise be hidden by the lack of data in low-density regions. In particular, it showed us that even a state-of-the-art AOD raw model trained on real raw images still has a considerable drop in person detection performance in extremely dark scenes if no gain adjustments are done. All in our Making the Discrete Continuous research, we build a flatter distribution for a fairer and more controlled evaluation using high-quality synthetic data only possible through raw image augmentations. By doing so, we uncover problems hidden by the resolution and constraints of real data, such as the reduced person detection performance of the state-of-the-art AOD raw model on low-light scenes with no gain adjustment. If you're interested in our work, please read our full publication and come see our poster in the Autopilot workshop at CVPR 2026. We will be grateful for any questions or suggestions made either in person or over email. Thank you so much for watching.